talk about some of the results we've obtained so far. It's still, there's still analysis ongoing. And then talk about the path forward. Okay. Here's a brief history of land use modeling. In the 1960s, you had a lot of economists and geographers who sort of popularized this monocentric city concept. Very simplistic, with land valued as a function of its distance from some urban core, which works pretty well in Paris, but not everywhere. And there were a lot of problems with that. And in the 1970s and 80s, which I'm calling the Doldrums period, there was some development of spatial interaction models. And I haven't used any spatial interaction models myself, except that I can tell you that the gravity model that is commonly used in travel demand forecasting is one form of a spatial interaction model. There was an article published in the Journal of the American Planning Association in 1973 called A Requiem for Large-Scale Urban Models. So this guy, Doug Lee, was saying, you know, they're dead. Don't even try it. The data is too messy. It's too hard to come by. To do it right, you really need much more computational power. And to a certain extent, a lot of that is still true today. Fortunately, we do have much better computers, but the data is still an issue. There was one package, DRAM-MPOL, that was popularized during that time, and that is still used pretty widely today. Now, in the 1990s, or late 80s really, there was renewed interest in land use modeling for a couple of reasons. One, the legislation, ICE-T, and then later on T21, which sort of promoted integrated transportation land use modeling. Then there were the Clean Air Act amendments and various environmental lawsuits where it became incumbent upon planning agencies who were seeking to expand highway facilities to demonstrate the impacts on the environment and land use in particular. And although the legislation didn't require integrated land use modeling, there was strong recommendations that that be done. So in the 1990s, you had a couple of other, some sort of landmark land use models, Trainus and MePlan. Both are based on an input-output concept, which has to do with sort of a regional economic concept of basic economic inputs being used for, or outputs being used for inputs in another part of the economy, and tracking that and linking that to travel. In the mid-90s, or late 90s, Oregon began its ambitious statewide modeling project, which we call TLUMIP, standing for Transportation Land Use Model Integration Program. And actually we have a couple of its primary, I wouldn't say architects, but people who helped develop it here in the room. And then there's also UrbanSim, which I'm going to focus on here. Currently, the state of what I'm calling the state of practice in land use modeling, regional planning agencies, most of them don't do it. And many of the ones who do it come up with their own ad hoc methods. Portland Metro has its own model. It's a somewhat aggregate allocation model. There's a lot of reliance in these agencies on what you might call official forecasts. So the state gives them a forecast, and they sort of to distribute it across their region spatially. So there's this trend extrapolation and spatial allocation. And that DRAM-MPOL model is still widely used despite many acknowledged limitations. So the cutting edge now is more micro-simulation of individual decision makers rather than just taking aggregate allocations of households and employment and just allocating it using some sort of interaction model. In doing so, they create what we call synthetic populations. So you are modeling individual households or jobs. It's now done at a finer spatial resolution. We're zeroing in on things like in TLUMIP 30-meter square grid cells. Okay, so that's like a quarter acre or something, about that amount. we're now trying to integrate the land use models with transportation models, and I've listed here for the more what I'm calling application-oriented research, because they're all sort of being developed at universities or by university-affiliated researchers, but they're being developed for clients, both in Canada and the US, and there's some in Europe too. Two approaches. The Tulumet model in Oregon, I'll just contrast the two because they're very, actually UrbanSim had its genesis in the Tulumet program, and due to various artistic differences, went one way and Tulumet went another way. Tulumet is a state-level model. It's integrated an activity-based transportation model, has an integrated regional economic model. It requires a lot of computational power, so it's done with parallel processing. And there's custom programs being written, and it's still under development and refinement. UrbanSim, developed by Paul Waddell at the University of Washington with a lot of help from the computer science department and graduate students, is a sort of designed for a metropolitan scale. Transportation model is exogenous to it, even though it's designed to be linked to a transportation model, which I'm going to show you, which we did in Honolulu. Things like the regional economic inputs are exogenous, so you have these control totals for households and for jobs. And the focus is more on the real estate market dynamics. So while it doesn't have the more holistic, comprehensive view that Tulumet has, it's easier to use. It runs on a PC, and you can download the software from a website. So that's why it's been used in not only Honolulu, but also there are implementations in Houston, Seattle, and Salt Lake City. So now the Oahu MPO Land Use Transportation Modeling Project is basically this. You see the nice island there. All those little green things are actually grid cells. There are almost 52,000 of those, and they're 150 meters squared. And the brown lines, I added them for contour. Those are actually transportation analysis zones, TAZs. And in its simplest form, this is all it is. You have your land use model, which is producing households and employment, jobs, spatially distributed across the region. They're fed into the travel model, just like other demographic and economic inputs you would put into a travel model. The travel model will produce some measure of what we're going to call accessibility, and I'll discuss that quite a bit, which then goes into the land use model, and that affects the way land is developed in the form of prices, in the form of location choices that households and firms make. So I'm going to just quickly review four-step travel demand modeling with feedback. Your basic four steps are listed here. You have trip generation, trip distribution, mode choice, network assignment on the left. How many in this room are familiar with this basic process? Okay, that's pretty good, about 70%. So trip generation is basically, very quickly, taking socioeconomic inputs and producing some expected number of trips for a zone within your urban region. You also produce expected number of attractions to that zone. In trip distribution, you're matching the trip productions from zones with trip attractions in other zones, and you're distributing them. And that distribution is affected by sort of the weight, or I would say the size of the attractiveness in one zone versus the other. And that attractiveness is diminished somewhat by the disutility of travel between them. So it becomes less attractive as it's further away. Then, of course, mode choice, you're making a discrete choice. Once you know where you're going, I'm going from this zone I to that zone J. How am I going to get there? And you apply a probabilistic model, typically, for mode choice, and you choose the mode. I'm going to drive alone. I'm going to share a ride with somebody. I'm going to take public transit. I'll walk. One of those. Once we know what mode you're taking, and we already know now that you're going from I to J, we're going to assign trips to the network for each of these categories The network, of course, there's a complicated algorithm involved where it's called user equilibrium, where users try to minimize the shortest travel time path through the network to get from their zone I to zone J. With feedback, I have this other loop here. You go down to where it says converged. With feedback, what we do is we'll run through this several times where we'll actually generate zone-to-zone impedance skims. In other words, that could be travel times or some composite measure, which I'll talk about in a minute. And based on that, we'll feed that back into the trip distribution step and then go back through mode choice and network assignment. And as we go through that again, we'll check and see, are we reaching some convergence? And by convergence, you usually develop some criteria like some maximum amount of change, between iterations to the volumes on the link. Or some people use travel times, and you also tend to look at changes to the trip distribution, the table that shows trips going from I to J, until that sort of settles down and there aren't too many changes between iterations. All right, this looks dangerous. I'll talk briefly about composite impedances and the disutility of travel because it's sort of a relevant concept to integration with land use modeling. I mentioned the mode choice model, and here's a simple view. There are your modes that you can choose from for this particular trip from I to J. And typically, the state of the practice now is to use a random utility model, which is a probabilistic choice model. And you'll see there on the right, under where it says multinomial logit, you'll have a model of that form. If you look at the exponentiated u in that term, that represents utility. As I said, these are random utility models. And so what we're actually attempting to do here is to measure the utility of the traveler for that particular trip from I to J. We're actually looking at the utility of each mode, and they're going to probabilistically choose one. They're more likely to choose the one with the highest utility. Of course, we can't observe utility. It's a concept, more so than a reality. So through estimation, we are able to estimate utility functions based on what we'll call indirect utility, which is the utility associated with certain attributes of the trip or the person or the travel situation. So in this function here, u, we have utility as a function. Well, there's a beta constant, but then there's variables that go into this, such as level of service to the transportation system, perhaps some socioeconomic factors that bias the choice a little bit, and there may be some attributes of the location itself that affect the utility of that particular mode alternative. An important concept in this is the idea of composite impedance, because when we talk about accessibility in terms of a land use model, what we look at is the utility, well, we're looking at basically the utility of travel for the particular between any pair of zones or grid cells or whatever it is. One way we get at this is we use our mode choice model, and for a given travel time, we'll come up with ij pair going from this place to that place, we'll calculate a composite utility. And the way that's usually done is using this blue formula here, which is you just take the denominator, that top formula, and you take the log of that. We call that a log sum. And that becomes a composite impedance. And believe it or not, there's this guy, Daniel McFadden, who won a Nobel Prize for using these types of models. But it can be proved that this log sum composite impedance represents the maximum expected utility for that particular trip. And because it's the denominator of that equation, it's taking all of those modes into consideration simultaneously and weighting them. And I just threw this graph in here because I wanted to illustrate that as your travel time goes in this direction in composite impedance, increases, your utility decreases. So we often talk about the disutility of travel. So here's the accessibility concept. So now we're sitting here, and we're looking at our land use model. And in land use models, we want to calculate the accessibility of this zone to other zones. One of the things that is theorized to be important to land use modeling, to the value of the land, and to the choices that people make in terms of where they locate is accessibility. And we talk in terms of accessibility to jobs, if you're a household, accessibility to the population, if you're an employer and you need people to come work for you. And so the way this is calculated in UrbanSim, and it's done similarly in a lot of other land use models, is a formula similar to that. This is a simplistic one, where on the left side, we measure sort of the size of the activity available in every, well, these are grid cells, so every grid cell, and it'll be some function of the number of jobs or the number of households there. So that's going to, and the way I have this, the darker shading, the more of those jobs or households are in the grid cell. So, but this is offset by the disutility of travel. So that Lij is that log sum that we looked at in the previous slide. So that's going to, so whereas you may get a lot of utility for going up to this zone because you can reach a lot of jobs or households or whatever your interest is, that's going to be diminished somewhat by the fact that this vector is, it's going to take you longer to get there. When we're calculating accessibility, though, as sort of a single value for a grid cell, what we do is then we sum up for this grid cell I, we sum up the accessibility calculations for going to all the other grid cells. And this is what's actually done in UrbanSim, and this is what's done in a lot of other land use models when they talk about accessibility. So in the Oahu case, what we did is to integrate their land use model with their UrbanSim, the land use model with the transportation model. So we basically just added another loop. We have the same loop with feedback for the travel model, but once it's converged and we now get stable results, we then calculate the log sums accessibilities, which we call skims. We use the term skims in travel modeling to refer to any table where we basically skim from the network the travel time or cost or what have you from one zone to another zone. So we calculate log sum skims, and we feed those into the land use model, which it then uses to calculate accessibility. And the land use model then will produce households and jobs by TAZ, Transportation Analysis Zone, that go back into the trip generation stage and are used actually in several other places within the travel model. Now, UrbanSim uses what I'm referring to as an agent-based approach to modeling. You're not allocating things in aggregate form. You're looking at individual agents. And very simply, you can break it down into 3 units of analysis: the grid cell, the household, and the job. And each of these is also represented in the model by an economic agent. The grid cell is represented by a developer, the household by the household, and the job by the employer. And it's actually kind of a bottom-up approach in some ways. The grid cell is kind of developing itself. There isn't this big landlord out there that has a whole bunch of grid cells that decides which one to develop. It's sort of a bottom-up approach where through the simulation, at each simulation year, we look at possible transitions for the grid cell from one type of development to another, or staying the same. And the same is true with the job. We're tracking individual jobs, yet it's as if some employer decides to move them. In effect, what happens is the job decides to move. So it's kind of a bottom-up approach in that sense. Grid cells look like this. In UrbanSim, they're at a grosser level than in Tulumep. They're 150 meters squared, which translates into 5.6 acres. And I overlaid this on some parcel data so you can see what it looks like in a typical suburban development. You get the sense of the size. I'll show you some more later. The grid cell have attributes. They are assigned development types. There are 25 development types, which I'll talk about in a minute. And with grid cells, you keep track of how many residential units are in the grid cell or how much non-residential floor area by type. We can talk about what year it was built, land value, improvement value, and any attribute you want to put in the database, really, for environmental and landform attributes, planning and zoning designations. You can specify all of these things for the grid cell. Households have the following attributes. They're sort of created in the beginning of the simulation through this synthetic process. Every household, as many households as there are in the whole region. And they have the attributes of number of persons, workers, age of head, income group, presence of children, race, and number of autos. Some of those are controlled for they're controlled by the U.S. Census, but some of the attributes such as presence of children and race and autos and age of head, I believe, come from PUMS data and are drawn from that. And the only thing that changes within the household is its grid cell location. Households are added, but once they're added to the simulation, they're added over time to meet regional control totals. The only thing that might change is where they are located. Similarly, with jobs, they're created, and jobs are defined by 16 industrial classifications and by non-home-based or home-based. And once those are created, and when I say created, again, they're trying to meet regional control totals for each simulation year. The only thing that might change with those is their location. They get assigned to a grid cell. Now, what can households and employers do? Well, in both cases, they have an initial location choice for a grid cell every time one is generated. And with each simulation year, there's a mobility choice. Do they move or stay during the simulated year? And if they decide to move, they choose a new grid cell. Developers, what can developers do? Well, it's actually the grid cell itself developing itself, really. You can have new development of a vacant grid cell or redevelopment of existing developed grid cell, which means it could change. It could go from sort of low-density residential to a higher-density residential, or it could become mixed use, or it could become anything, subject to land use plan types, which we code into the grid cells, environmental constraints, which we try to represent, and allowable transitions. You cannot, for example, go right from low-density residential to industrial. And there's a whole table of rules. So here's the sort of model dynamics for UrbanSim. With each simulation year, you have these series of 10 core models that are run. And actually, the way the software is specified, you can run them in any order, or you can run only some of them. So you have that option, but this is all of them. And typically, we start with accessibility. We calculate the accessibility, just as we talked about before, for each grid cell. So we know what its access is to the region, both for population and for employment. I should also add that when the log sum skims that we use in the accessibility calculations are stratified by auto ownership type. So for household accessibility, it's going to be different if you're a 0-car household or 1 or 2-car household. There's a household transition model, which is really just an accounting procedure. It looks at the regional control totals and says, well, we need to add some households or we need to take away some households, and it'll draw them from the distribution. The same thing with the employment transition model. Again, it's more of an accounting procedure than anything. Then there's a household relocation model, which is really, all that does is it looks and says, well, this household, which has a certain, it's based on income and the age of the household. Younger households tend to move more frequently, and depending on the combination of household age and income, there are different rates for transitions. Older people do not move as much. And with income, it sort of varies depending on where you are in your age. So, employment relocation, they use national rates basically for how frequently employers move. That's one of the things that's very difficult to get good local data on. And that varies by industry sector. Now we actually get into, when we get down to household location choice, we're getting back into logit models. We're not choosing modes, we're choosing a grid cell. So for all the households that said, you know, the 2% of them, or however many it was, that are moving during the simulation year, they then go put in the queue for household location choice. So with household location choice, you're choosing a grid cell, and I'll go into more detail on that in a minute. Then for employment, for each job that is to be relocated, there's a location choice step for that. After that, we update the land prices, and I'll go over that model in detail. And then the developer model kicks in. And the developer decides, based on all the data it sees in the database, grid cells, household jobs, vacancies, land prices, what the developer is going to do for a particular grid cell. Now I'm going to talk a little bit more about some of these models in detail. Not too much, though. The household location choice model, again, there's your friend, the multinomial logit. And in this, we've considered a number of explanatory variables. I did not specify this one, but it takes into account household size, income, things like cost to income ratio, things like the commercial square feet within walking distance, industrial square feet within walking distance, other residential units. And then at the bottom here, you have accessibility again, home access to employment. So what's its value for reaching workplaces? Employment location choice, same thing, except we have to do separate model for all 16 industry sectors. And you'll see there are a lot of variables considered there. Development type, bias constants, average land value within walking distance, different sector employments within walking distance. Depending on your industry, you may or may not want to be located to retail, next to retail or service sector. For some industries, being near a highway is important. Available job locations, that's a little bit murky. That has to do with how much space there is in a grid cell for a job, and there are predefined amounts of minimum square footage per employee that's defined in the model. And things like residential units within walking distance, that may have a negative effect if your industry type is industrial. And then again, at the bottom, accessibility, work access to employment. How much of the population can I reach? Then there's this land price model, okay? So this isn't the logit choice model. This is called hedonic regression, which is sort of similar to utility in the sense, if you think of hedonism. I don't know why I think of that. But anyway, what you're trying to do there is you're trying to measure the price of the land as a function of its attributes. So you can estimate a linear regression with this. And one thing that I'll point out is this term here with all the V's. That's those V's look, the V with the S represents structural vacancy rate versus the cell's existing rate, subtracting out the cell's existing vacancy rate at the time of the simulation, and looking at basically the percentage plus or minus that it's vacant, are different from the structural vacancy rate. So structural vacancy rates are input into the model before you start. So for example, I got estimates from this guy at the city of Honolulu as to what the vacancy rates should be for residential as well as for commercial and so forth. And so what this pricing model will do is it will adjust the price if a grid cell is too full. Okay, that's going to reduce its value. Is that right? Yeah. If there's a lot of space available, that will increase its value. And then, of course, we have all these other explanatory variables that are being considered in terms of calculating the price. I won't go into those. But again, we have accessibility. See, home access to employment and to population. Okay, now the developer model is like this. Once again, it's a multinomial logit, but what you're doing is you're starting with one development type, and then you're choosing another one. Actually, what you might do is choose the same one. In other words, you don't change. And the development types, there are actually, I've just listed them here by their basic categories, but then there are 8 different types of residential, 8 mixed use, 3 commercial, 3 industrial, government, and vacant. So for any given simulation year, you come along and you look at each grid cell and calculate basically its transition probability using a logit model, whether it's going to stay the same, vacant. I made that up, 92% chance it'll stay vacant, and then some percentage chance that it'll get one of these other development types. The explanatory variables typically used in that, there are a lot of sort of confusing constants in there, but land values, whether it's near a highway, proximity to other development types, and so forth. So in terms of implementation, in developing the model, there's a lot of data that needs to be gathered. Land use data came from parcel, from the tax assessor's office, parcel data and building permit data. You have census data from POMS and census tape files. Employment security, ES202 is employment security data, which will show you spatially how many employees are located at various employers throughout your region, although a lot of it is misleading. They tend to cluster things at headquarters, and then so the city of Honolulu did a lot of extra work, distributing, say, employment in the school district to all the different schools and to the post office, and from the Bank of Hawaii headquarters to the various branches and that kind of thing. A lot of it's supposed to be in the data, but it often isn't. And then, of course, there were GIS coverages, which we added, so we could give the grid cells attributes for steep slopes and wetlands and planning and zoning. And in terms of, I guess, estimating, calibrating models, there were 25 development types specified. Jobs were differentiated by employment sector, and households by household type. The way the model, this is some more detail. I won't spend too much time on this. The data, the information passing from UrbanSim then to the transportation model are predicted data, which we take the grid cells and we sum them up by zones. So households by attributes and joint distribution and employment sector. And that information updates in the travel model all these different components. There are highway network area type designations, which are a function of population and employment density. There's an auto ownership model, which is based on household attributes. Trip generation models. There's actually a visitor model for Honolulu, which uses hotel rooms. And then there's a truck model, which pivots off the employment data. So all of those are converted. I had to write some special programs to do that. And in going in the other direction, out of the travel model, you get the highway travel times and composite accessibilities in the form of mode-choice log sums. And those are used to update UrbanSim's accessibility model, land price model, location choice model, employment location choice, and developer model. And then we went through some integration and testing. And basically, I'll tell you that the travel model for OMPO takes days to run. It runs on an antiquated MinUTP software platform. It's just awful. But UrbanSim itself, you can simulate 5 years in 1 hour. Okay? That's pretty good. So what they asked me to do is just exchange inputs and outputs between at 5-year intervals. And first we just ran it to 2000 and we checked that. And then we went all the way to 2025 and it took weeks. Not because of UrbanSim, but because of the OMPO travel model, waiting for that to converge. As it gets more congested, it takes longer, more feedback loops. Okay. We're on schedule. So I'm just going to list sort of the key findings that have to do first with the land use model results. And these are in comparison to their existing inputs. They wanted to know, at this point, the current contract is plug UrbanSim into our transportation model. It was developed mostly by the guys at the University of Washington, although I did a lot of cleanup stuff. And run the travel model and show us what we get. So we want to know how different this is going to be than what we're used to. So this is what I found. With UrbanSim, you're getting general patterns of diffusion. You're having more mixed land use types, employment, jobs are now closer to residences. The local character of development becomes sort of blurred. In Honolulu, you have huge resort areas in Waikiki. And all of a sudden, you go through the simulation, and it doesn't distinguish resort or hotel from any other type of commercial. So it's putting jobs in all sorts of commercial sectors in Waikiki that wouldn't be there before, and the hotel jobs in Waikiki are sort of moving around to other places. There are differences in neighborhood household size that become blurred. For example, in the downtown area in Waikiki, you have a lot of small households, 1 or 2 people living in high-rises. And then there are those other neighborhoods where a lot of your larger families live. And so what's happening is you're seeing those patterns sort of diffuse and blur. And also mixing of industry sectors. Typically, for example, and this shows up a lot in the truck model, there will be certain industries will locate in a certain area. For example, near the waterfront, you have a lot of warehousing and so forth. And so some of that's moving out into other areas too. And as I mentioned before, now you have employment in the hotel sector going to places where it really wouldn't go, and other stuff coming in. There also is a capability to preset large-scale development events. So if you know that there's going to be this huge development at a particular location, you can program that in so it'll kick in at whatever simulation year it's supposed to take place. And I found that sort of imposes shocks to the system. Even it sort of needs to be smoothed over time and messes up the structural vacancy rates. And I also found that those accessibility calculations can be somewhat volatile. I looked at the differences between the 2000 and 2025 were pretty vast, partly because the whole area became so congested in 2025 because we didn't add any new highway capacity. And we didn't spread the peak. We didn't spread the peak hour over time like you would want. That it really affected the accessibility calculations. However, I consulted with my good friend who's the main travel modeler in Salt Lake City, and he had very different results. So more needs to be looked into that. This isn't UrbanSim. This is where I threw it into a GIS, and I color-coded the grid cells based on job allocation just to sort of illustrate things. And this area up here is right here. That's Honolulu. So that's downtown Honolulu, and this is Ala Moana Shopping Center and Waikiki. That's in Sand Island. It's industrial. It's shipping, warehousing. And I have the underlying parcel lines underneath so you can sort of see where people live too. And I guess I should have had this up when I was talking about the diffusion, but basically what you're getting is you're getting a lot of mixture of employment moving up into the hills, okay, up into the residential areas and forming new mixed-use development. And at the same time, you're having more residential coming in here. It's kind of interesting. It's not terrible in the sense that it's not vastly different from what you would see. However, it does have some effects. How it affected the travel model is as follows. Auto ownership, we have more zero auto households with UrbanSim. Although as I ran it over time, it's sort of balanced out. In trip generation, UrbanSim produces more attractions and it's better balanced to productions initially. You wind up in the net with more trips generated, a little bit, not a whole lot. In trip distribution, the average trip length is slightly shorter in UrbanSim. And in the district-to-district movements, the largest overestimate was a factor of 2.1, which is actually not as bad as I thought I would see. Most of them are actually fairly close, and you wouldn't expect them to be identical anyway. Now, all of this sort of gets back to the fact that basically now you have jobs closer to residences. So with mode split, there's very little difference in the aggregate, but you're getting slightly more walk and transit trips. Highway assignment, we're seeing huge differences, slightly fast peak travel times on 8 out of 10 facility types. And then in terms of vehicle hours traveled, 10% less vehicle hours traveled with the UrbanSim, 2% less vehicle miles traveled. There's less congestion because people are actually just not going as far. And that's mostly noticeable during the peak. There's really no difference in the off-peak. With the visitor and truck models, there are significant differences because it's not really recognizing, for example, port areas where the trucks have their transshipment facilities, and it's not recognizing the fact that you have these special tourist locations. So things are kind of getting messed up there. So issues and refinement, and then we'll take some questions. I discussed this at length with Paul Waddell, who's the sort of creative force behind this, as well as with gentleman from the city of Honolulu, Steve Young. And if we do a follow-up on this, what we're going to do then is, rather than just looking at the travel model results, we'll probably look at the individual land use model components in more detail. And the things we're considering doing is developing more specific development type definitions to account for military, agriculture, hotel, resort. I didn't mention, but UrbanSim was prototyped on Eugene, Oregon. So what's in Eugene, Oregon and seems broadly applicable when you look at it from that perspective really isn't when you go to a place like this, especially with the large presence of military and resort. And I think we want to break the commercial into sort of building types more, office, retail, and hotel. Maybe differentiate the residential. Right now it just talks about density, but maybe differentiate between single and multifamily. Distinguish between field-based jobs and building-based jobs. Location choice for agriculture isn't straightforward because many of them don't work in buildings. So it's looking for some floor area to put these agricultural jobs in. And so it's moving them to places where there is floor area, but many of these people don't work in buildings. Same true for military and construction. But even within those fields, of course, you do have people that work in offices. So the other thing is, in some of the choice models, incorporating what I'm calling same-type inertia effects by household size, so that we maintain the character of neighborhoods where they tend to be large family versus small household size. And the same with employment sectors. Steve Young at the city wants to consider smaller grid cell sizes, maybe as small as 1 acre, which would be about 64 meters squared. And if we're going to include these development events table, we need to smooth those over time. And in general, I want to evaluate the accessibility model and the way that's calculated, and maybe do some adjustment there so you don't get such crazy fluctuations. So at this point, I will take questions if anyone has any. Yes?
It was developed in Eugene, UrbanSim.
I think that was the first prototype.
And if you run the current, oh yeah, should know, but when you run UrbanSim on Eugene or on other cities for the current year, are the outputs, do they match pretty well with other simulation models?
Do they match with other simulation models? Well, I mean, I've run the UrbanSim version of Eugene, okay, that's actually comes down when you download the software, you get Eugene, the Eugene database, but I haven't compared it with any other simulation model, so I'm not entirely sure.
What about with actual data?
I've not looked at Eugene with actual data, but I'm quite certain that it matches up very well because that was their whole test case, what they calibrated on. Now, anecdotally, it's been run in a few other places, including Houston and Salt Lake City. And my friend in Salt Lake City, he found differences, and he did a lot of restructuring of the model specification. He started looking at each land use model component individually. He just forgot about the whole travel model impacts. Just started looking at each one specifically, and included new variables, new assumptions, changed a lot of things. I'm not sure it's more of a modeling environment and package than it is a model itself. I mean, the performance you get depends completely on the models you specify and how you calibrate. So,
okay, but I just wanted to really ask to see if the model actually if it mimics real world situations well. I guess maybe I could have just asked that more simply.
Okay. It does in places, and in other places it doesn't. And I'm speaking specifically, in Honolulu, there are some parts of the region where it seems to just nail everything, especially right in the center of the island, around Pearl Harbor, Pearl City. It just seems to nail everything. But then you get down to the fringes, and it gets really iffy. Yes.
You didn't talk much about your QA/QC process and just your modeling, and whether a QA/QC process changed the reliability of your model.
QA/QC process. When you're talking about QA/QC in this context,
well, maybe
what are you thinking?
The
quality of the data?
Quality of the data, especially some of the explanatory variables that you had incorporated into the model.
Okay. One of the things, I was not on board on the project at the time that these models were estimated. I was sort of brought in later and said, here, integrate this with the travel model and have fun. But what I did do is I looked pretty intensely at the relationship between, for example, jobs and the space available for jobs. One thing I've discovered, and this is true in all land use modeling, is that, because I have friends who do it for other things, but there's often a mismatch between these different data sources. For example, you can have land use parcel data that says in this area we have so many square feet of commercial, and then you have employment data that says nobody works there. That can't be right. Sometimes you have employment data that says you have so many 100 employees in this particular industry here in this grid cell, but you don't have any land use data that supports that. It's strange that way. And it may not be as black and white in that. It may be just sort of an imbalance. You can't really have that many employees if you only have 100 square feet. You can't have 50 employees, I don't think. Anyway, but there is a built-in check within UrbanSim where it actually has what's called a consistency checker, where it will go through all of the database tables and the model specification tables, and it'll look for things like that, and it'll give you all kinds of error warnings. In that sense, they tried to build some quality control into the process. However, in terms of the data sources themselves, there are obvious problems. I went through a lot of trouble trying to reconcile missing parcel data because if you look at parcel data, what you'll find, for example, tax map ID numbers get recycled and things aren't necessarily reported accurately in building permit data, that kind of thing. A lot of these models were estimated originally and calibrated based on those base year assembly of parcel data. So to the extent that that's any good, that affects your model.
John? If I could just add to your response.
Okay.
Because I was around when the first generation of UrbanSim was developed in Eugene and when the models were developed in Oahu, there were peer review panels set up in both cases to help Paul design the model system and to provide feedback as it was being developed. And there's still a peer review panel to review the work that's going on in Oregon. And there is a peer review panel in Hawaii. I don't know when the last time was that they met, but they were involved in the selection of the land use model and its initial development on Oahu.
And they've done that in Salt Lake City too. And I think if we do any redevelopment and the client will be the city of Honolulu rather than the MPO, they'll probably want to do peer review. Yes?
You noticed that the model didn't work very well in Honolulu because of the high tourism base of all these hotels that are different than other types of things. Have you noticed other types of commercial development that are targeted to certain cities that you've run it in other cities that would be considerations to use when looking at other types of cities? Does that make sense?
Your question makes sense. And no, I haven't run it a whole lot with other cities. The way the way it's defined currently, it's designed to be a very easy-to-use, off-the-shelf package with these specified development types. And it's just, they're defined by ranges of so many square feet of commercial or industrial or governmental floor area. And in a zone, because they're in a grid cell rather, because they're fairly large, you might also have residential in there too. So there may be some small component of residential. And depending on these different ranges, you define these development types. Well, that's good, but one of the problems that was noticed by Steve Young at the City of Honolulu is, when he accounts for these things, he looks at, retail commercial very differently from office commercial, right? So you're going to have a lot more service sector jobs located in the office and not in the retail. So that's why I was a little disappointed. We have all this retail in Waikiki supporting the hotel industry, and there's all these insurance companies moving in there, But, well, not literally, but there are a lot of jobs from the service sector going there. And so I wouldn't call it it's not a huge problem actually for the transportation model because they wind up generating almost the same number of trips. Well, retail is different, but the change isn't as dramatic when you look at it through the lens of the transportation model. It is dramatic if you zero in on specific areas and you see, that this district has changed a lot in terms of its character. And if it matters, it probably matters more in terms of economic and land use studies if they were to use it for something other than just transportation. Gentlemen, you had a question a while ago?
Well, there were two things that I was curious about. Most transportation models have land use elements to them that are built around transportation analysis zones, and those are determined by the transportation model, and they usually correspond with the intensity of development in an area. TAZs get bigger or smaller depending on how intense the development is. Mm-hmm. And since that framework is already in place, I'm wondering what was the consideration for overlaying essentially a two-plane matrix over a landscape rather than using the existing geography that's assigned to the transportation model that is already there. In other words, why use the grid cell approach instead of just using TAS boundaries to assign the land use characteristics to? So that's one question, just what in model development, why you did that. And then the second question, it has more to do with this result that you get where it seems that the model attributes behavior to people that's more utopic than people choose. We seem to make choices that are messier than the model makes would assign to us. Mm-hmm. And so in using it, say as a capital budgeting tool for whether or not if you distribute land uses a little bit differently, you would increase or decrease the amount of capital investment that the public has to make to support a city. Mm-hmm. Is that utopia kind of behavior that the model assigns to people significant enough that it would skew results that you wouldn't have much confidence in them for different simulations you might take?
Mm-hmm. Okay. Question one. The use of grid cells, the number of transportation analysis zones in the AMPO travel model is 762. And there are 51,771 grid cells that we overlaid. So when we impose the grid cells, what we've said is we're just going to look at this at a much finer level of resolution. That's mainly why that's done. And they have a uniform size, which makes certain other statistics easier to compute. The TAZs are all sorts of sizes. But all the results we have at the grid cell level, we can aggregate up to the TAZ level, which is what we do to feed it into the travel model. So that way you sort of avoid, by analyzing it at as detailed of a level as the data can support, assuming it does support it, theoretically you should get better results, and at least you avoid a lot of aggregation error. Interestingly, there have been some models that have been where they try to use actual parcels as the unit of analysis, the actual shape of the parcel. They do this in this model called PICUS in Sacramento. And that presents its own problems because as you're going through the simulation, then you have to, as land gets developed, there's parcel assembly for large developments, combining a lot of parcels, and how do you model that, as well as subdividing, going in the other direction. It's a lot messier, even though it might seem more intuitive at first glance. So using these uniform grid cells is actually kind of a very convenient accounting tool, and they're finer resolution than the TAZs. Okay, the utopian behavior question. By utopian, are you referring to this behavior which I sort of cited, where this mixing of land uses and people cozying up to employment centers and that kind of thing?
Yeah, that and the simulation results seem to indicate. I take it that you do many runs and then compare the results of those many runs against what's actually on the landscape, and it seems to shorter trips, mixing of land uses, people living closer to jobs, taking decisions that might seem rational, but people don't seem to take them. So, so if that's the outcome that the model is having in the base year, as you go forward in time and you're creating this future landscape, how much can you rely on, how much is that error? And if you run into difficulty getting people to buy into the future landscape because of the misassignment that's occurring in the base year?
Well, a lot of the recommendations that I made under refinement were basically in order to address that kind of thing. In other words, what you're saying is unrealistic behavior, and what I would agree with are issues that you try to sort out through recalibrating the models or respecifying them. So, for example, talking about changing the development type definitions, recognizing the fact that there are some neighborhoods that are going to be primarily populated by large families and others by smaller households, singles or two-person households, which are getting blurred, as well as those other things. And in terms of the accessibility and people, the model saying the free hand of the market's going to make you go here and you're going to live closer to your job, there are things you can do to adjust that. Just penalize accessibility even more so that doesn't happen. So, but because there's so many models working together and they're all feeding off one another, it's somewhat challenging. You push something in here and it pops out over there. So there are a lot of degrees of freedom. So it is a challenge, but again, that's basically what we plan to do if we do this follow-on, which we're planning with the city of Honolulu, is then, try to make it behave more like the real world rather than this initial run, which is just sort of seeing what's going on based on the initial model estimates.
And have you done any what-if simulations where you've changed the land use around and then used it as a comparative tool to compare different simulations of, say, future urban development patterns?
Change the land use around in terms of what, the zoning?
Yeah.
Initially, I ran it I was given this table of development constraints, which are roughly tied, supposed to reflect essentially what zoning does, but also tied to these development type definitions. And they were pretty loosey-goosey. And what I saw was, 10 times more blurring of all these things and people just going everywhere. And it, really bothered me. So I got a hold of the whole Honolulu land use code, zoning code, and I went through everything and I redefined everything so I could get it pretty tightly constrained. That still doesn't affect the location choices of employment and jobs, but it at least affects the way the land is developed. So, you don't have development going up into the green hills and just a lot of nonsensical stuff. So it can be constrained, okay, within those parameters. And I've seen what happens when it's not constrained properly. Whoever set up that table initially didn't do it right.
I'm going to have to, we've run over a little bit, but I want to thank John very much. And before we thank him, I also want to, this is our last seminar of the quarter. We'll start up again actually on April Fool's Day, April 1st, Friday, with Nigel Wilson from MIT talking about transit. So thank you very much, John.
You're welcome.
Evaluation.